Okay, guys, we are going to get caught up eventually, especially those of you who are in first block. This will be the second time in a row that you haven't seen me, but we're going to take notes over the next topic, and we're going to go back and do the lab that you guys missed out on last Tuesday. So we're going to talk about heat exchange during physical changes, or physical, phase changes in state. And so you should have these guided notes, and we're just going to take you through what some of these concepts as well as a few calculations. So if you don't have a calculator already, make sure you have one handy because we are going to do a few calculations with this. Okay, so the first thing you'll notice here on your sheet is this thing called a heating curve. And a heating curve, as you can see, is just a graph of temperature as a function of time, or it could be heat added. And in this case, it's going to be for a sample of water, going all the way from -20 up to positive about 140 degrees Celsius. So over a range of about 160 degrees Celsius. And the notable thing here are these plateaus. So these plateaus are where phase changes are happening. So below zero, just as you would expect, because H2O has a freezing point of 0, or a melting point of 0, you can call it either one. So below 0, it would be 100% solid ice. Above 0, up to 100, it would be all liquid water. And then above 100, it's going to be all steam or gas. But we have these plateaus that are important, that are happening at the freezing point or melting point and at the boiling point. So what are those plateaus? Those are where phase changes are happening. So first of all, we can start by saying that at standard pressure, all pure samples of boiling water are what temperature? Well, according to our little plateau here, we've got water and steam, so that's a mixture of liquid and gas. Therefore, it's right at the boiling point. It's at 100 degrees Celsius. So that's going to happen at its boiling temperature, which would be 100. Okay, and then all ice water mixtures, according to our lower plateau, are 0 degrees. So that means that every pot of boiling water, if you're at sea level and atmospheric conditions are normal, every pot of boiling water should stick at 100 degrees Celsius. It doesn't matter how long it's been boiling. All that matters is that there's still some liquid in there, as well as some gas that's been created. You can leave it on, if you have a big pot of water and you leave it on the stove for an hour and there's still some liquid left, that liquid is not going to exceed 100 degrees. By the same token, if you have a mixture of ice water or iced tea or soda with ice in it, whatever, it's basically a water mixture, it's going to be at 0 degrees Celsius. And of course, pure water at standard pressure is the only true, is the only time it's going to truly be 0 degrees Celsius. And it doesn't really matter, again, if you've got a lot of ice or a little ice, as long as it's well mixed, it's going to stick at 0 degrees Celsius. And the reason for that is because the energy involved in phase changes. So for example, when I look at what's happening here at the melting point, so let's say I have an ice cube and I drop it in a glass and I forget about it, I walk away, leave it out on the kitchen counter, it's going to, within a couple minutes, start melting. And so now I have a mixture of ice and water, and I'm at 0 degrees Celsius. So why doesn't it warm up prior to all the ice being melted? As long as there is some solid ice left, it's going to remain at 0 degrees Celsius. So why is that? Well, the phase change from solid to liquid involves breaking of hydrogen bonds. So if I have a chunk of ice and I zoom in on a couple of water molecules, those water molecules are fixed in pretty rigid positions with the positives and the negatives sort of lined up as close to each other as they can be in this ice crystal. And as I leave it out at room temperature and heat is added, these particles, which were just vibrating back and forth in place, start to gain enough kinetic energy that they will melt, which just means that they can break apart from each other. Maybe not directly in opposite directions, but they can at least break free of the hydrogen bonds enough so that they can start to flow and become a liquid and change positions and flow around each other. That process is endothermic, meaning it's absorbing heat. So yes, the room is continually adding heat to that ice cube as it's melting, but the temperature is not rising because the heat that's being added is going toward the endothermic process of breaking the hydrogen bonds. The melting process is endothermic. By the same token, if we get up here to this top plateau, we have that pot of boiling water on the stove. Why is it never exceeding 100 degrees Celsius? It's the same reason. Your water molecules in the liquid state are still pretty close together, and so to boil the water, you have to separate them completely to make a gas. That takes a lot of energy. So every time two water molecules in the liquid state are pulled apart, that again is a very endothermic process. So when you've got that pot of water on the stove, until it's all turned to gas, as the heat is being added from the flame from the stove, all of that heat is going toward breaking the hydrogen bonds in the water molecules. Or I guess more accurately I should say the heat is going toward breaking the hydrogen bonds between the water molecules, right? Because we're not talking about breaking the water molecule itself apart. Okay, so how are we going to describe the reason why the temperature is not changing? So for the reason why, we can say that melting and boiling are endothermic. And therefore they're going to absorb, they're going to absorb whatever heat is added. As long as those processes are still going on, they're going to be absorbing heat. By the same token, when we freeze ice, if we put something, a cup of water in the freezer, and the freezer is well below 0 Celsius, and it's going to drop from room temperature, say 20 Celsius, down to 10, down to 5, down to 0, but then it's going to hang out at 0 for a while. It's going to stick to this plateau for a while. And the reason it's doing that is because while we're absorbing heat from the water at the freezing point, the process of crystallization or freezing is one that is exothermic. So it's giving off heat, and so even though that water is giving off heat to the freezer, the process of freezing is exothermic, generating more heat, and so the temperature stays constant until all the crystallization is done and you have a solid block of ice. So we can then go through and say that freezing and condensing, which would be the opposite of boiling, are exothermic. So as long as there is some freezing happening, you can't get below 0 degrees Celsius. And then once you have that solid chunk of ice, now it can start to drop in temperature again. And that's what you see with this lower leg of our little heating curve. Okay? So we can say that every sample of water that contains at least a little bit of liquid has to be somewhere between 0 degrees Celsius and 100 degrees Celsius. Because the freezing point, if you have ice water that melting or freezing, depending on whether you have it out in the room or in the freezer, whichever one's happening, those processes will either absorb or release heat, keeping the temperature constant, keeping that plateau happening at 0 degrees Celsius. And the same thing is true up here. As we boil water, the temperature is not going to rise until all the water is boiled away, and then that steam can then go on and get really, really hot, which is why steam can be so dangerous. You can get burned by an iron very easily if you've got it set to the steam setting where steam is shooting out, because that steam can be a couple hundred degrees, whereas boiling water can only be 100 degrees. So looking at the heating curve, which is this guy, so it's temperature versus time. And if we look at what the plateaus represent, we just pretty much talked about this. The plateaus are phase changes. Now the slopes, of course, just represent temperature changes, right? So the slopes we have from -20 up to 0, and then from 0 up to 100, and then from 100 up to 140 or whatever. So they're just temperature changes. So temp changes. Okay. Now, the important thing here to note is the steepness of these slopes. So why do you think that for these three slopes, so while water is ice, and then while water is a liquid, and then while water is a gas, I think you can kind of see that as a liquid, the slope is the least steep, okay, of these three. In other words, the blue line has the least, has the smallest positive slope of the three where the temperature is actually changing, where you actually have a slope. And it should make sense to you why that is, because if you think about it, which physical state is water going to have the most difficulty changing temperature? In other words, in which of the three physical states does water have the greatest specific heat or resistance to temperature change? And you should answer in the liquid state, right? It's like 4.18 if you go back to the previous worksheet that I gave you. 4.18 joules per gram times degree Celsius. And then as a gas, it's like 1.87. As a solid, it's 2.06, I think, right? So the steepness of the slope has to do with the specific heat of the state that it's in. Okay. So how do we draw a heating curve for water being cooled from 85 degrees Celsius down to negative 20? So here's how I approach these problems. Put your starting temperature, and we're just sort of, we're just roughly sketching this. It doesn't have to be perfect. We're not using real, graph paper or anything. I just want to say, okay, where's it starting? Where's it stopping? And then what's it going to look like in between? In other words, is it going to go straight from 85 down to negative 20? And you should say no, because what happens in between? Well, at 0 degrees Celsius, you have a phase change, right? So you already know that there is going to be, yes, a slope as it gives off heat and cools down to the freezing point, but then once it hits that freezing point, it's going to plateau for a while before it continues down to negative 20. Okay, you don't have to be too picky about the slopes or any of that stuff, as long as you understand that there's going to be three parts to this thing. It's going to cool down to the freezing point, it's going to freeze, and during that time where it's freezing, it's not changing temperature, and then it's going to cool down again down to negative 20. Okay. All right, so let's do some calculations. And you're given this table, and I'll show you how to use that in just a second. We already know how to calculate the amount of heat involved in changing temperature from like 85 down to 0, or 85 down to 50, or whatever, because we know the specific heat equation, right? And the specific heat equation, you don't have to write this down, but it's Q equals specific heat times mass times change in temperature. So that would be useful for figuring out what kind of heat is exchanged when the thing cools down from 85 to 0 or whatever. Anytime there's a temperature change, a delta T, right? But we're talking here about heat exchanged during a phase change, and we've already established that there is no delta T. There is no temperature change while a phase change is happening. There's a plateau, right? So we have to have a different equation. So the heat of fusion is how we describe the amount of heat released as a liquid freezes or absorbed as a solid melts. We already talked about the fact that freezing is exothermic and melting is endothermic, right? So we are going to be using a little equation here. It's a very simple one to answer a question like this, and it's just going to be Q. So once again, heat gained or lost equals mass times heat of fusion. So fusion is involved anytime we have a solid. So if we're going from solid to liquid or liquid to solid, so melting or freezing, we're going to use heat of fusion. And so if you look over here in our table that I've given you, heats of fusion given to you in joules per gram is right there on that table. So it's just a matter of essentially plugging in your mass, which was given to you in the problem, making sure you have the right substance. So if it's saying ice, that means water. And then plugging in the heat of fusion, and for water, the heat of fusion is 334. Don't worry about the fact that it's repeated 3 times. The heat of fusion really only matters when you're changing from liquid to solid, solid to liquid, but it's just how it shows up on the table. So 334 joules per gram is the heat of fusion for water. So if I want to find my heat absorbed, heat is Q. The mass is 25.6 grams. And the heat of fusion for water is 334 joules per gram. So then we get out our calculator. Go ahead and give that a shot, calculating that. Okay, and so I get 8,550 joules. Okay, and that's rounded to 3 sig figs. The heat of fusion is not something that I'm going to look at for sig figs because that is a constant, but the 25.6 has 3 sig figs, so that's why I rounded where I did. Okay, then we get into heat of vaporization. Basically, heat of vaporization is just the upper plateau on our graph. So it's the heat released as a gas condenses or absorbed as a liquid vaporizes. So it's essentially this plateau, whereas heat of fusion involves this plateau. So anytime a gas is involved, whether it's a steam or a gas cooling down and condensing into liquid, or a liquid boiling or vaporizing into a gas, you're going to be dealing with heat of vaporization. Okay, so HVAP is going to be essentially the same equation as up above, only this time it's going to be mass times HVAP. And we're going to be using a different number from the table. Our heat of vaporization is this last column. Okay, so if I do this problem, how much heat is released as 15.6 grams of ethyl alcohol condenses? It's just a matter of plugging in the mass pretty much and finding the heat of vaporization for ethanol. So Q equals 15.6 grams. The heat of vaporization for ethanol is, if I come up here, ethanol is 879 joules per gram. So go ahead and take a second, pause the video, and calculate that, please. Okay, so you should get 13,700 joules as our answer this time. All right, how many milliliters of sweat, assume sweat to be the same as water for the purposes of this problem, will cool your body down by 25,000 joules? So milliliters, if we're assuming sweat to be water, 1 milliliter equals 1 gram. So what I'm really trying to answer is mass. So if I have Q equals M times HVAP, okay, and remember the reason I said HVAP is because we're talking about how does sweat cool you? It doesn't cool you by melting on your body. It cools you by evaporating, vaporizing, going from liquid to gas. As it leaves your skin, it cools you down. So we're not going to be using the heat of fusion this time. We're going to be using heat of vaporization. But this time we know the Q value, right? So we know this, and we know the heat of vaporization because it's on the table, and we're trying to solve for mass. So mass, if we rearrange the equation, should be equal to Q over H of VAP. So go ahead and see if you can solve this one. Okay, so there you can see I plugged in my 25,000 joules on top, my heat of vaporization from the table, 2260 went on bottom, and I got 11 grams, which if we then recall that water is 1 gram per milliliter, would be 11 milliliters. Okay, so one more problem using heat of fusion, heat of vaporization. How many moles of silver could be melted using 465 kilojoules of heat? Okay, so go ahead and see if you can come up with the version of the equation, rearrange, what am I trying to solve for? Is this Q or is this mass that I'm trying to solve for? Okay, so if we're looking for moles of silver, then we really are trying to find mass, and then we can convert that into moles. So we already established that mass is equal to Q over H vaporization, but it would also be, in this case, because we're melting, it would be heat of fusion. Okay, so go ahead and see if you can get your mass of silver. Okay, and hopefully you notice that it was kilojoules. 465 kilojoules would make it 465,000 joules. And so it gives you a pretty big number of grams of silver, 5,284. So then go ahead and convert that to moles using the periodic table. Okay, so At this point, you should have your moles calculated using the periodic table. So just dividing by the molar mass of silver, which is 107.87, and I get 49.0 moles of silver. All right, so let's move on to the back side here. We're going to combine specific heat calculations, which you should already know how to do, with phase changes. All right, so I've given you kind of like a rough graph there to draw, or to draw a heating curve on. It says if we've got water going from 50 up to 125, what we're going to actually do here is, just like earlier I mentioned, writing down your starting and your ending, and then any phase changes that happen in between. So what phase change happens in between 50 degrees Celsius and 125 degrees Celsius for water? Right? So you should have said that it boils at 100, right? So, and that's not to scale, but that's okay. So it's going to go up to 100 from 50. It's going to plateau for a while as we boil it, and then it's going to go up again to 125. So we actually have 1, 2, 3 different things that are going on here. We have 2 times where the temperature is changing, parts 1 and 3, and then 1 time where we have a phase change. So let's go ahead and do those off here to the side here. So anytime the temperature is changing, like in step 1, we're going to be doing a specific heat problem. So we're going to be using that equation because we have a temperature change. If we have a slope, we have a temperature change, we're going to use this equation. So let's go ahead and just plug in the numbers. So we're solving for Q. We don't know Q. We do know the specific heat because it is liquid water at 50 degrees Celsius all the way up to 100. So that would be, according to the table that you got last time, 4.18 joules over grams times degrees Celsius. A 200 milliliter sample of water is going to be 200 grams. And if we're going from 50 up to 100, that's a change in temperature of 50 degrees Celsius. And so you're going to get that answer, which is 41,800 joules. And then we move on to step 2. So step 2 is where the water's boiling. So we're not going to be using specific heat because the water's boiling. We're going to be using the heat of vaporization. So it's just mass times H vap. And again, I know it's vaporization, not fusion, because I'm at the boiling point. If I were at the freezing point or melting point, I'd be using fusion. All right, so this time it's going to be the 200 gram mass times the heat of vaporization for water, which is 2,260 joules over grams times degrees. I'm sorry, joules over grams. Got my units mixed up. And this should give us 452,000 joules. Generally, phase changes are pretty high temperature, or joule amounts compared to just changing temperature. Phase changes are have more heat involved in them. All right, and then if I look at step 3, which is this last little leg here, from 100 up to 125, that's going to be a specific heat times mass times delta T. Now be careful here. You're going to be tempted to use 4.18 again because it is still water. But if you remember, water in the gas state has a different specific heat. And again, that's on the last worksheet that I gave you. You have all those specific heats. And actually, it's also up above on this worksheet as well. And you can see water as a gas is 1.87 for its specific heat. Joules over grams times degrees Celsius. Mass is 200 grams, and our temperature change is 25 degrees Celsius. And if we multiply those out, we get 9,350 joules. And if we want to know what all of these together, in other words, from 50 all the way through the boiling process and up to 125, what all of those together would be, we're just going to add up these 3 numbers. And so it's going to be 41,800 plus 452,000 and also 9,350. If I add all those up, I should get 503,150 joules. And as far as significant figures are concerned, we are adding up our answers here, but we're not going to follow the rule for addition because these aren't measured numbers; they were calculated. We're gonna go with the rule for multiplication division because what we did with our measured numbers, our 200 milliliters and our two temperatures, is we multiplied them, or multiplied, at least the mass and then the change in temperature. So we're going to go with 3 sig figs, and that should be 503,000. Okay. So what I'm going to ask you to do with the rest of your time here is try these last 3 problems. Now, before you do each problem, you want to draw a heating curve, which is this thing with the temperatures. Make sure you mark any significant temperatures where there's a phase change, as well as your starting and your ending temperature. Some of them may be going down; they don't all have to be going up like this one is. And I will make the answers available to you, so you can check those out.